This problem is a strategic decision about which container handling equipment a terminal should invest in. The choice shapes the cost structure, productivity, environmental footprint, automation potential, and the ability to adapt to demand and vessel mix. We compare three primary options: rubber-tired gantry cranes, rail-mounted gantry cranes, and straddle carriers. Each option has different strengths, and a defensible decision must connect investment cost to throughput, storage density, and long-term operational flexibility. Mediterranean Container Terminal is planning a $200 million expansion. The terminal currently processes 2.5 million TEU annually and expects to reach 4 million TEU within 5 years. The expansion site covers 50 hectares and includes 8 container blocks, each 400 meters by 150 meters. Landside throughput is about 3,000 moves per day, and rail connectivity handles 15% of total volume. The team evaluates 3 candidate configurations. Option 1 is an RTG-based system with 16 cranes. Option 2 is an RMG-based system with 12 cranes plus rail infrastructure. Option 3 is an automated straddle carrier system with 24 units. Key cost ranges are $8 to $15 million per RTG, $12 to $18 million per RMG, and $3 to $5 million per straddle carrier. Operational productivity ranges from 15 to 35 container moves per hour, and stacking density ranges from 4 high to 7 high, depending on equipment and layout. We will move tier by tier through different decision methods. Tier 1 uses multi-objective Pareto optimization to represent conflicting goals explicitly. Tier 2 uses constraint propagation with backtracking. Tier 3 uses artificial bee colony optimization. Tier 4 uses federated learning to leverage distributed industry data while preserving privacy. Tier 5 uses a digital twin. Tier 7 emphasizes a human and artificial intelligence Centaur model. Tier 8 adds a value-aligned ethical framework. Tier 1 treats equipment selection as a multi-objective problem. The objectives include minimizing total cost of ownership and maximizing throughput capacity. The model also includes maximizing stacking capacity and maximizing operational flexibility. Because these objectives can conflict, the solution concept is not a single optimum, but a set of Pareto-efficient solutions that represent different trade-off choices. The set of equipment types includes RTG, RMG, and straddle carriers. The planning horizon is 20 years and the terminal is divided into 8 container blocks. Many parameters include capital and operating costs, productivity measured in moves per hour, stacking capacity, flexibility indices, and demand by block and year. The main decision variable is the number of units of each equipment type assigned to each block. A second decision variable indicates whether an equipment type is selected. This is used to enforce policies such as selecting one primary system or restricting assignment decisions to a chosen configuration. The first objective is to minimize total cost of ownership. It combines upfront capital cost with discounted annual operating cost across the planning horizon. This net present value structure makes the model sensitive to operating expenses over time, not just initial capital expenditure. The second objective maximizes throughput by combining productivity per unit with the number of units, scaled by operating hours. The third objective maximizes stacking capacity by capturing the storage contribution of equipment across blocks. The fourth objective maximizes flexibility by summing flexibility indices for the selected equipment type. The model enforces selecting one equipment type under a single system policy. It also enforces capacity requirements so total throughput meets peak demand. Logical constraints connect assignment quantities to the chosen equipment type, and a budget constraint ensures total capital expenditure stays within the available investment budget. Decision variables are restricted to non-negative integers. This comparison matrix summarizes equipment alternatives across important dimensions, such as cost, productivity, automation readiness, stacking density, and operational constraints. The purpose of the matrix is to show that equipment selection is not only about unit productivity. It is about how the technology fits the terminal's operating model, land constraints, and long-term sustainability goals. In the simplified example, RTG has $12 million capital cost and 0.8 million per year operating cost, with 22 moves per hour and flexibility index 0.8. RMG has $15 million capital cost and 0.6 million per year operating cost, with 30 moves per hour and flexibility index 0.3. Straddle carriers have $4 million capital cost and 1.2 million per year operating cost with 18 moves per hour and flexibility index 0.9. The reported Pareto set includes 3 non-dominated configurations. A pure RTG solution uses 8 units with net present value cost of $156 million and 1,408 moves per day capacity. A pure RMG solution uses 6 units with net present value cost of $162 million and 1,440 moves per day capacity. A hybrid straddle-centered solution uses 16 units with net present value cost of $134 million and 1,152 moves per day capacity. Tier 2 applies backtracking to explore configurations systematically. Constraint propagation prunes infeasible combinations, early by updating feasible quantity ranges based on remaining budget and required capacity. This is valuable when the decision includes discrete choices and interacting constraints, because it avoids evaluating a large number of obviously infeasible branches. This diagram shows how the algorithm expands a search tree and prunes branches when constraints are violated. The key idea is that each partial assignment can be tested for consistency, and the remaining search domain can be reduced before deeper branching is attempted. This code defines a consistency check that verifies total cost is within budget and total capacity meets the minimum required capacity. It also defines a domain propagation step that computes remaining budget and restricts quantity ranges, so the algorithm does not try quantities that are not affordable. This section implements recursion. If there are no remaining decision variables, the algorithm records the assignment if it satisfies constraints. Otherwise, it propagates domains and prunes if there are no valid extensions. It then selects a variable and tries quantities within the feasible range. This portion shows the outer solve function. Define quantity ranges for equipment types, execute backtracking, and collect all feasible solutions. Finally, it ranks solutions by a composite score that combines multiple criteria, so decision makers can see the best trade-offs among feasible options. In the example with 8 blocks, the terminal requires 2,400 moves per day capacity and has a $180 million budget. The algorithm explores branches for RTG, RMG, and straddle systems. It tests multiple unit counts, pruning infeasible choices and retaining feasible options that meet both budget and capacity requirements. The reported ranking includes 16 RTG units with total cost $176 million and flexibility score 8.5 out of 10. It also includes 10 RMG units with total cost $174 million and productivity score 9.2 out of 10, and 24 straddle units with total cost $158 million and versatility score 8.8 out of 10. Tier 3 uses the artificial bee colony algorithm. Each solution is a food source representing an equipment configuration. Employed bees explore locally around their solutions. Onlooker bees select among solutions based on fitness. Scout bees reintroduce diversity by replacing stagnant solutions, helping the search avoid local optima. This figure illustrates the flow of employed, onlooker, and scout bee phases and how solutions evolve over iterations. The important takeaway is that the algorithm blends exploitation of strong configurations with exploration of new configurations when improvement stalls. This section defines algorithm settings such as colony size, number of iterations, and an abandonment limit. It also defines how the initial population is generated using random counts of RTG, RMG, and straddle carriers and random block assignment arrays. This section defines the multi-criteria fitness function. It combines a cost score based on budget usage, a productivity score based on throughput relative to a target, a flexibility score based on diversity, and a sustainability score based on the share of electric or partially electric equipment. The fitness is a weighted sum, with productivity receiving the highest weight in the illustrated formula. This section describes the employed bee phase. Each employed bee modifies one parameter and compares the new solution to the current one. If the new solution has higher fitness, it is accepted, and the trial counter resets. Otherwise, the trial counter increases, tracking stagnation. This section describes the onlooker B phase. Onlooker Bs use roulette wheel selection based on fitness to choose which solutions to refine. This concentrates effort on promising solutions while still keeping probabilistic exploration of weaker ones. This section describes the scout B phase. If a solution does not improve beyond the abandonment limit, it is replaced with a new random solution. This mechanism is crucial for escaping local optima and maintaining diversity across the colony. This section presents the overall optimization loop. Run employed, onlooker, and scout phases, update the best solution, record fitness history, and stop early if there is no improvement over a sliding window. Operationally, this creates a practical meta-heuristic that can deliver strong solutions without exhaustive enumeration. The reported run uses colony size 40 and 500 iterations and converges after 284 iterations. The reported optimal mix is 14 RTG units, 6 RMG units, and 8 straddle carriers. Total cost is $178.4 million. Daily capacity is 2,856 moves, and fitness score is 0.847. Sustainability index is 0.72 with 60% electric or hybrid equipment. The reported comparative result is that the algorithm finds solutions 15% better than greedy approaches. It is also reported to be 8% better than simulated annealing in equivalent computational time. This indicates the algorithm's balance of exploration and exploitation is effective for this search space. Tier 4 uses federated learning to train equipment recommendation models across multiple terminals without sharing raw operational data. Each terminal trains locally and contributes updates to a global model using federated averaging. This approach leverages collective intelligence while preserving privacy. This architecture shows multiple terminals training local models and sending model updates rather than data. A central aggregator combines updates into a global model that captures patterns across the network, such as which equipment configurations perform best under certain traffic mixes and land constraints. This section defines a global model and client models. The base model is a feed-forward neural network that maps terminal features to probabilities over configuration classes. It also outlines how features are prepared from operational records, including variables like annual throughput, peak moves, traffic mix, yard area, budget, and return requirements. This section defines one-hot encoding for equipment configuration so that historical decisions can be used as training labels. It also defines local training, where each client clones the global model, trains on its local data, and evaluates validation accuracy. This portion defines aggregation weights based on validation accuracy and data size. Clients with better validated performance and larger datasets contribute more to the global update, which improves robustness of the aggregated model. This section defines federated averaging, where each parameter in the global model is updated as a weighted average of client model parameters. This produces a global model that integrates evidence from distributed terminals. This section defines prediction, where the model outputs confidence values for each configuration type. It also defines a strength rating for recommendations, classifying results as strong, moderate, weak, or not recommended. This section defines a full federation round, local training, global aggregation, and evaluation across clients. It computes global accuracy based on test sets and can be used to monitor whether the global model is improving over rounds. The reported network includes 12 major container terminals and runs 15 federation rounds. The global model achieves 89.3% accuracy in equipment selection recommendations. The MCT profile includes annual throughput growing from 2.5 million to 4 million. TEU peak 3,000 daily moves, truck share 75%, rail share 15%, yard area 50 hectares, a $200 million budget, and a 12% return requirement. The reported top recommendation is a hybrid configuration with 74.2% confidence, rated strong. RTG Pure is 18.1% confidence, rated weak. RMG Pure is 5.3% confidence and not recommended. Straddle Pure is 2.4% confidence and not recommended. The reported recommended hybrid mix is 10 RTG units, 4 RMG units, and 6 automated straddle carriers. Tier 5 reframes equipment selection as a living system rather than a one-time decision. The digital twin models equipment performance, traffic flow, weather effects, maintenance scheduling, and economic optimization together. It runs continuous simulation cycles and uses real-time data feedback to adjust equipment deployment and identify bottlenecks before they degrade service. This architecture integrates IoT sensor streams, RFID and GPS tracking, weather data, and financial systems. Machine learning calibrates model parameters, and an optimization engine recommends reallocation or investment changes. Multiple scenario models run simultaneously to support rapid what-if evaluation. The reported system processes 2.3 million data points per day from 847 IoT sensors. It increases average crane productivity from 22 to 26.8 moves per hour, reduces unplanned downtime by 34%, and reduces operational costs by 12% through energy optimization. The digital twin supports dynamic deployment strategies. During peak season, it recommends a hybrid configuration with temporary RTG deployment. During off-peak season, it supports RMG-focused operations with straddle carrier flexibility. Under vessel clustering, it activates straddle surge capacity. Under maintenance windows, it reallocates equipment to preserve service. It also reports that a hybrid plan avoids pure RTG bottlenecks and saves $23 million over 10 years. Tier 7 emphasizes that equipment decisions require both computation and human context. AI systems can evaluate thousands of scenarios and integrate large data sets. Human experts contribute local operational nuance, relationships with shipping lines, regulatory constraints, and strategic market interpretation. Explainable interfaces make AI reasoning transparent and support collaboration. This figure shows the Centaur model structure for equipment selection. It emphasizes transparent reasoning, tailored explanations for different stakeholders, and trust-building mechanisms. It also highlights collaboration points where uncertainty is high and human judgment provides the most value. In the example, the AI initially recommends a pure RMG system based on efficiency. The terminal manager notes that short-sea shipping and smaller vessels require higher flexibility. The final hybrid is 60% RMG capacity, 25% RTG capacity, and 15% automated straddle carriers. The hybrid achieves 94% of the pure RMG efficiency and is reported to outperform human-only and AI-only decision-making by 18%. Tier 8 treats ethics as first-class constraints. Equipment selection affects jobs, worker safety, emissions, and community health. A value-aligned approach models stakeholder values explicitly and prevents unacceptable outcomes, even if they appear cost-optimal in the short term. This framework figure shows ethical constraints layered on top of operational objectives. It supports multi-stakeholder optimization that balances worker impacts, environmental justice, service quality for customers, and long-term sustainability. The reported worker impact differs significantly by equipment choice. RTG systems require 150 operators, RMG systems require 80, and a hybrid requires 110 with retraining programs. RMG electric systems reduce local air pollution by 85%, while a hybrid with electric RTGs achieves 70% emission reduction. The value-aligned optimization selects the hybrid despite 3% higher cost and includes $2.3 million for retraining, plus community health monitoring and profit sharing. Reported stakeholder support is 89% worker approval, 94% community endorsement, and 76% investor acceptance.